let it get cold. I've been experimenting. Yes, I know it's all backwards, but what it is the lube chart. Recommended lubricants for a 310 case crawler. In this case, literally a loader crawler. Well, what I'm doing is mobile printer. This is an HPRT. Yes, MT810 thermal printer. And what was the idea of buying this for? Well, one of the things is to have a printer, thermal paper, it's in a roll. I don't know if I can control the size of it yet, because as you see, it goes oversized quite a bit. However, reading, pretty good. Pictures, well, I tried one of our lovely niece, Robbie. It came out good for dot matrix and black and white. Beautiful young lady, mom, nurse. I've been having trouble. If you connect direct, everything seems to go through. I've been trying to get the Bluetooth thing working. Well, without realizing it, because the instructions are fairly poor, there's an app to download, and I've had trouble for that. Printing from Windows PC. Use a cable. Download printer driver from the website and install it on the PC. Huh. Well, I guess I'm going to have to try and do that later. But I had to connect. So I have some more reading to do to see. But so far, as you saw there, this thing has done well. Now, it's been sitting in the car for the longest time, because what I do is, let's see if it'll shut off on me. There we go. I got to charge it up again. It's been sitting in there because I haven't had a reason to actually go print, and I have a box of specialized tools in there. Let's see, what did I have in there? Borescope, extra multimeter, some specialized electrical fuel line tools. What else? There seems like there's something else odd in there I'm drawing a blank on. I'll remember later. But there's some specialized tools I have in there, and I threw this in a box because it's a nice closed plastic box to handle everything. Well, and this works with diesel laptops when I plug it in direct through the USB. I did a live before, and it didn't. I got some numbers mixed up. Now, let me see if I can do this time. We'll start with hydraulics, even though I have it written here. Let's start with nomenclatures and such. All right, now, I didn't write it backwards, so you're going to have to read it backwards. Pi, 3.1416. D, diameter. R for radius. Now, this is when we're talking our hydraulics. PSI, pounds per square inch. For those that don't know, GPM is your flow in gallons per minute. And those are the figures that we're going to be using. Down below is some formulas we'll play with in a little while. Now, what I am looking at here as far as hydraulics is you can have your basic system. What the heck, I got paper here. You will have a pump. And the nice thing about hydraulics is flexibility. Now the pump, if I draw it this way, this is a symbol for a pump. Actually, this is a symbol for a compressor. The triangle is white, pointing in the direction of flow. If I fill it in to make it dark and black, this is now a fluid or hydraulic pump. Connect a reservoir. Well, there's two types of reservoirs. There's the common one that's vented, and then I'll put below it a non-vented. Or I should say one is open, and then there's above surface, below surface. Okay, there's your different reservoirs if you're going into symbols. There's your closed sealed reservoir it'll have a vent, but this is your open, like a transmission housing or a tank that doesn't have a specialized vent, just a cap. That's above surface. Or actually, no, return would be above surface, if they show a return in the tank. So you know this is always in the bottom in the fluid. But if it's a return line, that would be above surface, this would be below surface. They do something similar in this one as well. So we're talking suction. Either one of these two will be fine on the suction line, or low pressure as you purists like to have. What's the flow rate? Well, we don't care yet. Now I'm going to draw a square. I'm going to do this with a little simplicity. Now I got to be careful when I'm drawing the picture here. We'll do a single acting cylinder just for the fun of it this time. Now why am I doing a single acting cylinder? Well, I'm drawing it wrong, let's put it that way. That'll also add to it. But you'll get the idea. Let's see, raise. Lower. Alright, anyway, this is poor, and I'm doing it on the fly. What do we have here? Well, I'm doing two reservoirs just because. You fire the thing up, oil's going up, out the pump. This is your relief valve going back to tank. Over here for your single acting cylinder, now you notice this is a loop. Well, that is your pump going back. These are the same tank. Don't. Now, for raise, then these two are going to get connected and raise it. It's in hold now because it's blocked. So there's your raise, there's the cross line, and then there's a blocked off return port. Over here, I drew a little angle doodad so that it would look like this one connecting to the return line. And that's the idea. It's as simple as it gets. Now, how fast does this raise? Well, that's something else altogether. How fast? Well, we don't know. Let's just say you have a 10 gallon a minute pump. So now you have both flow rate, GPM. Now you have both flow rate. So 10 gallons per minute. Now you got to start dividing into how much per second, or how much time per gallon. So it's roughly 6 seconds, isn't it? Per gallon. 10 times 6 is 60, correct? And that's what we're looking for. 10 in that 60 seconds. So every 6 seconds, you have a gallon. Well, let's just say your cylinder is 2 gallons. You got to fill 2 gallons to go all the way to the end. You have 10 gallon a minute pump. Every 6 seconds is a gallon, correct? So it's going to take 12 seconds for that thing to raise, to fill the 2 gallon mark. We're done. So now you've got speed without a problem. Well, how much power is it going to have? It depends on your relief setting. Your average one, let's say, is 1,000 pounds. Okay, 1000 psi, pounds per square inch. That's what it's set at, and you're going to measure in the gauge. Now, there's always a break off in the line where you're going to plug something in or put a T in, or in this case, a quick coupler, where you could disconnect the cylinder and put it in there and then activate the lever. And it'll deadhead and blow the relief, and then you'll know how much. But you want that at an idle, very much at an idle, just to know, just to near near as possible to the cracking pressure as you can. In industrial commercial stuff, they're almost always full bore all the way to the line. So what do they measure there? They measure full flow relief, because that's what's going to be happening. No matter what you want, full flow relief is the critical one. So let's just say you're figuring out the area of your piston. You already know you have 1,000 psi. Okay, you're figuring out the area of your piston. Now, I botched it up the last time I did this and put it on here live, and what it is the diameter of a circle is pi times d. Right, yeah, the circumference of a circle is pi times the diameter. Okay, 3.1416 times the diameter. So if the diameter, say, is 5 inch, you know you're going to be just over 15 inches, almost 16 inches. Let's do the calculating for fun, since I'm sitting right here looking at it. Sorry about the glare in the glasses, but I'm too cheap to do anything different. Here we go. No, I don't need that one. I need not that one either. Not that one. I need this one. There it is, calculator. 3.1416 times, what did I say, 5? 15 point, almost 16, 15.708, 15.7. So yes, you are near 16. If you're doing calculations at home and you're not doing calculations for industry, you know you're going to be able to guesstimate in that case 16, just like I did. 15.7 it comes up. So if you want to make yourself feel better, run the calculator. Obviously it's not hard. So now I know the circumference of the circle. I'm looking for power. Okay, how much? Well, let's say it's still 5 inches. Let's go back. What is area? Well, I'll show you the formulas. Where are we here? Flip this thing over. Circle, diameter. Pi times the diameter is going to be your circumference. Yeah, I wrote diameter. Circumference. Gives you an idea how often I use these formulas. Almost never. We used them a few times when I was at Anderson, where people wanted to know certain things. But now the area of that piston is over here. Here's your pi times the radius, r, squared. Okay, squared, what's that mean? Well, for those of you that know, plug your ears. For the rest of you, squared means if the radius is, in this case, 2.5, half of the diameter. Diameter is side to side, all the way across, straight line. Radius is center out. So radius is from the center to the outer boundary. That's going to be 2.5 times 2.5. You could find the square. What? In fact, they have it on here, 6.25. Let me clear that. 2.5. There it is. There you go. And you see up top there is pi. I'm going to hit pi. Pi times the radius squared. The total comes up 7.8539. Now, let's do this. 2.5 times 2.5, because it doesn't have the square root up there. 6.25. Now hit pi. That comes up different. Alright. 6.25, because we know pi r radius squared times pi. 6.25 pi comes up 19.634, basically 19, let's just say 20 square inches. Well, that's interesting. So we have 20 square inches, right? That's what we were doing before. That's the face of it. 20 square inches. Now what? The actual symbol for that is if your IN is an inch squared, then it gives you the surface area. So the surface is 20 square inches. Great. Now you put 1,000 pounds per square inch. And again, we're not in engineering, so we're not playing with the points. You want to know roughly how many tons this log splitter is going to push out. We have 20 square inches with 1,000 pounds per square inch. That's 20,000 pounds. Just add the zeros. Literally true. How do I know? Because you have 1,000 pounds per square inch, and there's 20 of them. That's the idea. Now, you have 20, what's that in tons? 10 ton. You have a 10-ton log splitter. Divide by 2,000. You end up 2,000 into 20,000. Well, you've got 3 zeros in both. Slop the zeros off. 3 of them in each. So now you got 2 and 20. 20 divided by 2, 10. That's simple. That's the old school way. Did you write it down and follow it through? Well, that's how you're going to learn. So there we go. We have a 10-ton log splitter now. That's with 1,000 pounds on a 5-inch cylinder. Big thing. Well, they all run 2,500 pounds. So you're talking 1.5 times this on a 5-inch? 25 ton? Woohoo! That'll get something done in a hurry, baby. Don't overthink this. Don't overthink this. That's exactly what it is. What's the other problem? If that cylinder and rod are not designed for that 2,500 pounds, you've got a real problem now. Something's going to give. But still, that gives you an idea of, we just found out that it's going to take, what did I say, 12 seconds for the thing to go all the way to the end on a 10-gallon minute pump and a huge cylinder, 2 gallons. And at the same time being 5 inches, so this is a long cylinder most likely. And it fills with 2 gallons. It takes 12 seconds of time out. Your return time is far less than that because the rod takes up quite a bit of the space. So your total time is probably going to be in the neighborhood of 15 to 18 seconds, depending on how much flow, the restriction in the lines, your pump, your engine, and all of that. So now you know your cycle time. And you know how strong it is. And you sat down with a piece of paper and figured it out. And you can have all that before you put your log splitter together. Or lift cylinder for your brush hog, your hay bine, or whatever else. It's that simple. So, those are things to keep in mind playing around with hydraulics. Now, another thing that causes problem with all of this is what I talked about before, is we had one that was an 856 International. Now, this is going aside from all of this stuff. Yes, Hobie, I know you're there. Got my little dog underneath me saying it's time to go to bed, Dad. Because I've been off schedule since Debbie's been down in the Keys. Now, one of the problems in maintenance is people don't change the oil very often or run the machine long enough. Now, there's several problems I've learned over the years that causes trouble with water in these hydraulic systems. You got a nice flat tank with a beautiful flat surface, and you got a cap. The cap's vented from the bottom to keep rain from going in. Beautiful thing, right? Well, it depends on how much space you have. You want that cap to have about a 1/2 inch to 1 inch gap, because rain's going to come down, splash, and go up in there. I said, well, big deal. No, it sits there. And then heating and cooling, it'll suck that stuff right up in there. It'll end up in there. So what's another one? Snow. Even if you don't run it, believe it or not, the sun beating down on that metal cap and the snow being on there, and the heating and cooling cycle will suck that water right up in there. If no other way, in that stainless steel mesh that's up in there, capillary action will walk right up there and drop it right in there. So if you don't run it often enough, you're going to have to change your oil. There's no other way to get the water out, either by heat, boiling it out, or just plain vaporizing it out from using it. And the other one is change the oil. Tractor we had the other day, to give an example of how important it is, as soon as I opened up the back, because we were looking to find out why it only had didn't have enough pressure to lift up the hay bind. So I have gauges and connectors and took it up there. Didn't take but one gauge and one connector. We had a 500 pounds at idle and 1,000 pounds at full throttle. Didn't even check anything else out. That's it. That's all we did. Plug it in, ran it. He gave me the signs and symptoms that they have. Hay bind lifts. Hay bind suddenly doesn't lift. Hay bind lifts half throttle or above when it's cold. Well, that's up near the 1,000 psi. Lifts pretty easy. Now, you have it at idle. Write it down, just like I am. Idle. I'll put an I, 500 psi. Record this stuff because you're going to forget it. Full throttle, F, 1,000 psi. Okay. What have you just done? Well, if 1,000 psi at full throttle and 500 at idle, you already know you have an immediate problem with building pressure. Immediately there's something leaking somewhere. It's just that simple. Immediately. How do I know? A, without even looking up the pressure, I already know this tractor is someplace near 2,000 psi. It's old, in the 60s. They didn't tend to go up over 2,000 very often. This one actually was lower than I thought it would be, I think, but I'm not going to tell you that yet. So 1,000 pounds early in the day will lift his hay bind. Actually, anything probably 700 to 800 pounds, 1,000 pounds, because he's not going up on the throttle, but halfway, he said. So minimum, he's hitting 750. Minimum to raise that thing. And he sometimes has to go full throttle, and then once he warms anything up to any extent, it's over. It'll never raise, which means it's below 750. But the difference is you're at idle 500, full throttle 1,000. If at full throttle you're running 1,000 psi, at idle it would normally be about 900 psi. So you don't even need to know the real pressure. You already know that there's a problem in the system. You could say the relief valve's working, but it's set wrong. If it's at 1,000 and then you pull the throttle back near idle, then it drops off to 850, 900, somewhere in there. You know, you're doing pretty good. The pump is generally working. You probably have a problem somewhere else, and you haven't even gotten any further. Well, here, you haven't gotten any further. You already know there's a pump problem instantaneously. Something's leaking off somewhere because you can't build a respectable amount of pressure, and going to idle, whatever it is, it drops way off. So there's a huge leak in there at building pressure. What's pressure? Flow is active. It's oil moving through the system. That's your flow. Pressure is the restriction of oil moving through the system. You could call it workload or anything else, but pressure develops when there is a resistance to the flow of that oil. That might be carrying a weight, that might be an orifice, that might be a valve, but that's the idea. So, while we're looking at that here, 1,000 psi, 500 psi, immediate problem. So what do? On the 856, this one makes it easier. You take 3-point hitch, top link plate off, right above the PTO. You pulled that off, fired the tractor up. Oil's just, we didn't even go above idle hardly. Oil's flowing, just flowing right out of there, right down into the reservoir, right behind the bull gears. I thought, well, that's kind of a strange place, but that's what we expect. I pulled the lever, and we were checking the pressure on the gauge. As soon as I pulled the lever, the oil flow totally stopped. Completely 100%. Well, now follow me. From the pump is on the left in front of the left axle. Right down on the bottom. Runs off a gear, one of the drive gears going back to the PTO system, as I remember. So it's constant. And it goes up a port in the housing to the mating surface with a top cover. Goes across and into the valve. Now it might go at an angle or something, but still it comes over and goes into the valve, and the pressure relief valve is right there. And it's on the back right corner. So the port goes over there. Yeah, close to the back right corner. It's just a little bit forward of that and under the seat. So we had oil coming right out. As soon as we opened this, coming right out of the housing, right where that we expected it to be in that valve in neutral. As soon as I pulled that lever, no more flow. None. There was no leakage. Almost 100% total stopped. I'm going to say 98%. There was a little trickle someplace. Just a trickle. If the relief valve had been bad, it'd have been blowing out of it. Nope. Problem. So what do we do? Well, when I looked in the housing, there was already enough water in the oil that you couldn't even recognize it as oil. It looked like bad milk. Somebody poured molasses in, just a little molasses in. It was nasty, and it swirls, and so it's like, yep, your pump's junk. He says, just that easy. Yep, pump's junk. How do you know? I told him about the differentials and the pressures. And I also told him that when I pulled that lever and we're supposed to be blowing relief, that oil has to come out back into the housing. He said, oh crap. Yeah, it didn't. So we got a problem here. He says, yeah, I would say so. About a week later or so, he pulls out the pump, brings it down, and we tear it apart. And I'm pulling pieces out one by one, and things are shiny. There's hardly anything scratched, but there's a lot of shiny pieces in there. Well, what happened? It was steam cleaned. There's enough water in the oil, and while he brought it over, it sat for a little while, and inside the suction port was water, paraffin, and a little bit of oil. They separated. Well, that's bad. Couldn't even carry that much water. And there's almost as much water in paraffin as there was oil. If that gives you any indications. So that's one of the places. And what did that do? It steam cleaned the interior. The pump body itself was okay. Now, each side of the gears, there's two gears, and they mesh and roll together. And as the gears teeth come out, that's suction. And on the other side, as the gear teeth go in, that's pressure, because it pushes the oil out into the port. So when I was a kid, I used to think it worked like a sawtooth and run it right through the middle. No. As it opens up, it sucks the oil in, brings it around the outside, and then squeezes it out over here. So it was all steam clean and shiny. But to keep the gears more efficient, they have bronze plates on there, brass. And one side is fixed in the housing. The other side has a labyrinth seal behind it with a Teflon ring up against the steel plate because that gets hot. And the rubber seal is behind it. And there's some ports in there. So the pressurized oil goes under through the labyrinth and pushes the gears, squeezes them together. More pressure, more efficiency in general. So that seal was blown. I mean, the Teflon hadn't even come out, and there's a rubber seal sticking up in there between the gears. Almost. So it's like, yep, I found your problem. And it was blown out in several areas. So what happens when it blows out? Well, it's under the gears. It just blows out around the seals and goes into the shafts and into the suction side. Pressure goes to the opposite side. Then the vacuum side, the low pressure side, high to low. Just logical. So we had a pump that could have been serviceable, but I told him I didn't trust it because it was probably a reman pump and it had markings of it. And in a reman pump, sometimes the housings, if they don't have to machine it and it's within a particular spec, they'll fire that thing up. And if they can get the flow and pressure rate that they want, as well as open flow rate and full pressure, and then the test is in between, how close is the flow when you get that close to relief. So if it's 2,000 pounds here, you bring her up to about 1,900, 1,800, and see what your flow rate is. And it should be about 90%. It's going to back off a little bit as everything has some slippage to it. But that's the idea of testing the pump. And if for international, and when they're rebuilding these things and it makes it, out the door, nobody cares. Well, if it's worn too far, then that also can cause that rubber problem there. But I'm thinking with the water in there, it just hyper pressurized it with steam and just blew it out. That's what I'm guessing, the way everything looks so shiny. It was something. So we had a pump that might have been serviceable with a kit. The kits are half the price of a pump. You buy a pump. Unless one's not available. So that's the basic fix on that tractor. However, I also added with Luke, my customer, because he was doing the work, I was doing the diagnostics for it, or assisting him in it, and helping him understand and learn. And I told him you got to change the oil twice and change the filter twice. Don't put the same filter in there now that it's water impregnated. Do not do that. And the other one was replace, you put a pump in, you put a relief in. Every possible time. Every time. Why? It's a guarantee on the pump. It's a guarantee on the pump. That's all it is. Because there's too often that something sticks. Sometimes on some of the two-stage pilot operated relief, you could get a kit and rebuild them, but that's a lot of time. And anymore, when you're charging $75, $100 an hour, the dealer's $150 an hour. Yeah, it'd take an hour to 2 hours to actually clean one up properly and put it back together. Let me tell you, just buy the dang valve, because you're going to get $300 in that thing fast. $250 to $300, and the valve's costing $3 to $5. Put the valve in. Oh, you don't want to pay for it. I know. If you're at home, that's your deal. Or if you're working with people like Luke and I, and you make that decision, we can do it for you. Yeah, we're cheaper. You could probably afford it then. We ain't guaranteeing nothing. Your system went bad. Well, what do you think that water did to it? Well, just like we had with that pump, the interior, anything brass or copper, etched badly. And it was starting to actually peel off the bearings, taking the brass coating off of it. Can't help you. It's already bad. Separating the brass from the steel backing on either one. So you're screwed. Now, next thing. We got through the hydraulics and killed that enough. Next one. Oh yeah, electrical. This is one of my favorites. I play around with these things. Need glasses again because of the way we got it. And yes, it's backwards. Okay, V is for volts. A is amps. Ohms is your measure of resistance. So why I don't know. I could put ohms in there, but you want resistance. Trust me. Just get used to it. So, a couple of formulas. Volts equals amps times the resistance, or ohms. But what are the ohms? Ohms are the equivalent of the volts divided by the amperage. The amperage is the inverse, volts divided by the resistance. Well, times, then divided by. Just that simple. Because if you want to get rid of the R, you're trying to find the R, you know the A. Maybe the A is 3 amps. Well, divide it by 3 amps. Cancels those guys out. Divide the volts by 3 amps. Now you have your resistance. Okay? That's how those systems work. You have 12 volts, 3 amps. Well, you want to know the resistance. 12 volts divided by the 3 amps. You have 4 ohms resistance that you're looking for. I know, your volts are going to be different, 14 volts or whatever that you're measuring. If you want to measure it with a machine running, then do that. Measure it with a machine running. And then use your figures there, and then you'll come up with maybe 3.5 amps. Is it really worth it? Get your basic numbers and then start your troubleshooting from there. Now on the other side, watts. That's a whole nother deal. That's an idea of how much power usage there is. Now you're talking your lights on your old tractors are about 35 watts. So you have 35 watts. You know you have 12 volts. Well, you're looking for the amps. 35 watts divided by the 12 volts. Roughly. What is it, class? Exactly, 3 amps. That comes up 36 watts. Close enough. You're messing around with a system that you say, if you start averaging in, say you're putting 12 lights on the unit, now your 0.2 amps or 0.1 or whatever might be a factor. But if you got a dozen lights, you know every one of them is going to draw 3 to 4 amps each. Well, then go to the high side. You know you're going to have 48 amps of service. You're going to need several lines. So it changes the whole scope. If you want to run it all off of one line, you're going to have dang big wire in there, Betty. Let me tell you. You're going to be setting up your system with multiple switches, multiple fuses, and multiple lines to keep the size down. Why? The main reason you're going to do that is if one goes bad, the others still work. And the fire is a lot smaller and a smaller wire. Trust me on that one. So that's what we're doing with watts. Same idea. So if you don't know your volts, but you have an idea of the watts, and you're measuring amperage, well, you can figure your volts out. Now, another one I didn't cover in a lot of this is voltage drop. I've gone through it and done it by resistance. And one of the things you can do, I showed it on the other one prior, but yeah, let me just draw the light. Oh, it's a beautiful light. You've never seen anything like it. Okay. Minus. Then I'll put a switch on the plus side. Two things you can do here. Here's a funny one. All right, I'll try to hold it higher. What you're going to do is turn the thing on, and it's dim. Voltage drop you can measure. I'm going to hook on here first, starting the positive line. Almost always the problem is right here. But let's start on the positive line. You're going to believe it. You hook your, I do believe you hook your red one here and then go to here. If it says 0 or 0.1, if something under half a volt, use volt range or millivolts even. You're good. Keep this one connected. Now jump the switch. Jump all the way to the end. Now switch it. Hook up to your negative and run your positive down the line. If there's different connections, then that's your voltage drop. Will tell you where the problem is. 9 times out of 10, the problem's right there, or here, or at the connections here. So sometimes you just walk up, clean them up, put them together, and problem solved. I've done that before without ever doing any troubleshooting. Why? Because you ought to do it anyway. I got in trouble in high school for that, or in college for that. He says, it won't start. Okay, so we walked over. We knew where the neutral switch was. We reached in there and pulled the rubber cap off. The wire is disconnected. He blew a cork. You aren't supposed to do that. I said, what? Physical inspection's the first thing you're going to do in your troubleshooting, isn't it? He got mad. I wanted you to use the meter. The next kid says, that's not what you said. You smart mouth a little, and old Gordy Walsh lost it. But true story. Do your physical search first. It's a lot easier. Now, another way you can test this thing that's a different way. Take these two wires off and connect them together. Disconnect these from your power source. And then put an ohm meter across them and see if you're down below 2 ohms. On a 12-volt system, they can handle about 2 ohms. But still, you're better off closer to 1. On a 6-volt system, you better stay down to 1 as close as possible as far as line loss. Okay, the other way you can do it is leave your light in there. If you can calculate the resistance on your light, or don't, just disconnect here, turn the switch on, and when there's no power, set your ohm meter on and see what the total resistance is. And then look at the light and see what it's supposed to be for watts. Then you can start doing your calculations without ever farting around with the thing. But your voltage drop's a lot easier. What's your voltage drop across here and here when you're disconnected from the battery? Or even when you're connected to the battery, I should say. 12. What's the voltage drop from here to here? 12. If your engine's off. Yeah, this line should have almost no loss in it. So you still should have, the total loss here is going to be 12. When you back up to here and you're reading voltage drop kind of thing, it's going to be a little less. But it should be 11.89 something. But this is your total voltage drop here. Just something to keep in mind. Ohms is the resistance to the flow of electricity. Voltage is the force or the pressure behind moving the electricity. The actual the actual output source, the juice you're looking for, is measured in amperage. The amps actually creates the magnetic field as the electrons flow. The magnetic field in the wire is an electron flow going to the light source. So the amps are what's lost on the way through, or is never lost. That's the funny thing. Amperage is never lost all the way through the line. Voltage is a voltage drop. It's used up. And if it isn't, you got a dead short and bad things happen. Anyway, that's another one that you don't even need anything for. But the formula helps. If you know what the juice is at the battery, then you know you have a 35 watt light, or 2 or 4 or however many's in the system. Now you have an idea of what you're looking for resistance. Or in some cases, amperage flow. If you don't know any of the above, and the system isn't blowing a fuse, flip the switch on and start going across the connectors to test what your voltage drop is at a particular point. Because if it's bad enough, you're going to see potential difference between 2 points. Because there's a disconnect. Anyway, that's the idea. That'll be the negative circuit could go to the light, through the light, and back to the switch. But if the wire's broken before the switch, from here to here, no voltage drop. Stay on this one, or even start on the back side of the switch. Now move over to the light, first light connection. All of a sudden you have 12. Yes, that's because there's a break in the line. It doesn't get back to ground. If it doesn't get back to ground, the light doesn't use it up. Voltage drop. Electricity. There's an idea for you. Well, they got a fancier term. Loads. I guess they call everything loads anymore. In hydraulics, they're often called actuators. Your cylinders and such. Your motors. So, in electrical, it's often called a load. Now, a motor load, that's a different thing altogether. You can still use your voltage drop to figure out what the problem is there. But motors tend to have some inductive trouble. They'll start making funky noises when there's too much resistance on the line, and often you can feel the heat in the line. Because being an inductive load, it actually tries to draw as much amperage as humanly possible. So you may get a case where the motor that has voltage drop, as we call it, and is still trying to draw the amps, especially on DC loads, things start to cook. So just something to keep in mind. It's not the same as a resistance load. Resistance load, the resistance goes up, it stops or slows down, and it doesn't care. The heat, how can you say the light is the heat using the electricity up in the filament with the resistance there. If there's too much resistance in the line, then the amount of heat gets spread out. So sometimes you can actually take a temperature wand first, a gun, and go around through, and you might be able to find it that way. Same thing with hydraulics with restriction. You still got the pressure, it still wants flow, but if it gets a restrictive point, one of two things happen is often heat builds up here, and then afterwards it cools down, just like any other air conditioning system. You have force coming in, putting pressure on the oil, warming it up. Then after that, it's a drop-off. Just something to keep in mind. And often there, you can just take your hand along the lines. Again, you're better off with a temperature gun at first to see how hot the system is so that you can put your hand on it without getting burned. Hydraulics can go to 150 degrees without a problem, so the outside of a rubber line is going to be running over 100, and outside of a steel line in a 150 degree system is going to be 120 plus. You're going to get burned at some point in time when it's the plus. Just to give you some ideas. And anything electrical, once you get past your 15 and 20 amp circuits, and even there's enough amps and volts and such, you can get burned if you're not careful. That's why it's better to go through and do your visual inspection first. Anyway, that's Pops for tonight on electrical and hydraulics. I didn't bother to cover the similarities because we talked on them. Pressure gets the oil to it. There's always a pressure drop, but your oil itself is like the amperage. That's what does the actual work. Oil does not compress much, 5%, so they consider it uncompressible. It's not like pneumatics or air where you can compress that right down to. And when it lets loose, if you've ever seen 150 pounds all of a sudden blow something off and send it 100 feet across the yard, or you've chased an air hose around the shop that the fitting blew off, but the coupler and the fitting are still together, and that thing comes whipping around, hit you in the head, that'll be a memorable occasion for the next 6 weeks. When you get a bone bruise and a knot. Yeah, pneumatics can be dangerous. Hydraulics tend to go and it's all over when it blows. However, when there's a pinhole, you can get injection injuries. And you may not even know it, but usually there's a little sting, like a prick or something. You think, oh, I found a piece of wire. Maybe not. And anything over a few hundred pounds of pressure can, well, actually anything over 50 or 100 pounds can inject you, depending on your hands and the condition that are in at the time. The leather gloves help, but do not count on it. I've done it before when I was suspecting a leak like that, where I just laid a rag over something, fired the unit up, and it turned out that what they said was a small spraying leak turned out to be a spraying gusher. And the rag protected me because it hit the rag and the rag folded around it. And it just sat there and oozed down to the ground. So you use those things to know for safety. Plus your glasses, plus your gloves, plus you be careful with hydraulics. You're out in the farm tractors, no, it's not as big a problem as we had in the skid steers, backhoes, loaders, and other things where 3,000 pounds was a minimum for the things to even function. And excavators, 3,000 is nothing in most of them. Many of the professional excavators on the, say, a 7 or 8 ton on up through, they'll run 4,500 psi, and some of them as high as 6,000 because some jackass from Anderson, Syracuse will jack them up to 6,000 operating. Oh yeah, I really came alive then. How come the pumps went out at 2,000 or 3,000 hours? I don't know. How come we have overheating hydraulic trouble? I don't know. True story. Pressure is heat. That's all there is to it. Moving oil, heat. Moving oil under pressure without any restriction other than the load, heat. So, things to keep in mind. Electricity is similar, but you're looking there at some type of resistance loads, or worse yet, dead shorts. If you have a short, there's all that amp flowing through there. Whew. You can melt a wire down, melt a harness down. What a mess you can have. So be careful, because it doesn't matter the size of the wire. For a millionth or even a thousandth of a second, you can have a 500 amp surge, even in a small, say, 12 gauge wire. In a 24 volt system, it even gets uglier because they run a lot of 20 gauge and 18 gauge wires. With the voltage, they don't need to run the high amps to get the wattage into some of their inductive systems, your motors and such, and actuators. So it's something to keep in mind there. 24 volts can cause a disaster very fast, especially at the batteries. When you have two batteries capable of 1,000 to 1,500 amps each, they may be in series, so that doubles the volts and it maintains the same amps that each battery has, but you're still talking 1,000 to 1,500 amps. And you hook it up wrong, it's 2,000 to 3,000 amps. That's a bad disaster on a bad day. Know your numbers, know your connections, know what you're looking for. And for the love of your own life, please do not allow the bosses to send you out anywhere on any of the modern machines without at least a wiring diagram or schematic, and the same for your hydraulics. You need to know the specs, you need to know the location of your actuators, switches and such, even valving and everything in your systems. You need that information. If you have to, fight for it. Because you can go out, and if it's going to cost you your job, yeah, get in your truck and just drive. Get out of there. But at the same time, you need that information. Don't shortcut yourself. Unless you know you have a computer with the information in it. Start your troubleshooting without it. Write down the specs. Go to the book and find it. Now, there are times that things are bad enough that you need to know specs beforehand. And you'll have to gauge that. But make sure you have the specifications with you somewhere. Good specs, good working specs to your serial number. Because it can change drastically. Why? In the electrical systems and the new ones, they have those things called POTS, potentiometers. Some of them are simple, just a variable resistance. Some of them are signals. and they're split. One goes up, one goes down. And because it's a control side where your levers and such are, they're measuring the volts. One goes up, one goes down, millivolts. And on the other side, the actuator, they're measuring milliamps being put out. And they may or may not be two. Usually, two are on the control side. And then on the actuator side, that's where you get your single going to your actuator. Single wire out, and then your ground wire back. And either side could do the controlling. You have to be careful because some of those actuators, like injectors on some of the engines, are hot all the time, and they use the ground side to run the thing. True story. So be careful and know what you're working with. Anyway, the horse has been beat to death. Y'all enjoy it. I didn't even have to get into Howie Ferguson with this one. But if you're going out in the field too and you can con your bosses into it, this helps you as much as anything else. Battery operated, thermal printer. You just put a roll of paper in there. And you hit the button a certain number of times. Well, that's not the one, because I was playing around trying to make this thing work. Well, if you hit the button right, you get this beautiful picture out of there. But that's a different thing. That's my niece. Don't mess. Anyway, and then you get this out. It gives you the model and serial number here through your QR codes, and then gives you the basic specs for the machine. You know the printer's working. So you can do a test print. And sorry to say for some of you, because you're going, I ain't gonna do that crap. You get something like this. What was it? $80, $100. And if you like paper copies, find it on here. Run it out the printer. How hard can it be? Now here's a funny thing. I may not be able to do anything but hook up with a wire to the laptop I have from diesel laptops, but I can plug in the wire and print out certain specs. It's a lot easier to read, have it in the cab, you don't have to have the computer. I can take the tablet. This tablet has about 12 cracks in it already. Do I want to take that out on the road? Probably not. But I can do it on the phone. The phone automatically had the app download and try to update. So I can actually put the thing on the phone where you have a hard time reading it, or run it out on the printer. HPRT, that's the one that's here. And I've had it since August, September. Yeah, I haven't even had the chance to hook up the diesel laptops. I had somebody that said, yeah, bring it in, we'll hook it up. And then when I got in there, all of a sudden, jackass feet. Got cold feet. Well, what happens if it ruins us? How in the world is it going to ruin it? It's diagnostic. If the machine computer doesn't like it, it shuts it off. Yeah, but I don't want to. Yeah, one of those. And they were trying to figure out why in the world the shop was going down the toilet. And people were getting bad attitudes. I had an idea. And that was one of the better attitudes in the management. I was trying to do that so we would know how it would read, being down here in Appalachian and my employer 45 miles away. It made logical sense that if somebody called, either the night after I left or the morning or just before I left, I have diesel laptops, drive on the way home, stop and get a readout. Or get up in the morning, go out, get a readout, and go to work. How could you lose, right? I get a little extra time and they get a little extra information earlier than sending somebody else. Oh no, all of a sudden cold feet again. And it was their original idea. Yeah. People run scared the funkiest way. So sooner or later here I've been going out knocking on doors, hooking things, just talking to people, and sooner or later I'll find somebody that gets to the point where, yeah, I need this, and we'll be able to hook it up and get her to work. I think I have one that will allow me to do it sooner or later, but I just made contact, so we'll talk later on about it. And there's still a lot of farmers here that don't have anything with much for electronics at all, not even a simple common rail system. So unless you get into the compact tractors, and even there, if you're 25 horsepower and below, regular old jerk pumps, they're not even in the system for EPA. Doesn't matter. It's kind of funny. Anyway, there we got it for tonight. What have I got in here? Almost an hour, like 55 minutes of this. I'm going to try and cover some of this stuff a little bit more on and on and on. I'll probably pull in a meter sometime and see if we can get a read on the thing and go through these things, because some of the kids out there, you're not getting this education even in college. You can go to SUNY Coby Skill and some of the others. Right now, the debate between Alfred and Morrisville, because Alfred started their program up again, and you know they're going to be hot on for a while, and then they'll fluff and fall off later. Coby Skill went in the tank because they were dumb. The higher-ups decided to hire somebody, put him in the position there at the college with a PhD and no practical experience. I came out of there with people that were winning awards for teaching with other colleges, sending back and saying, thanks for sending this guy up here with all this information. They could take 2 years at Coby Skill, 2 years at Cornell, and then they'd have their 4-year Cornell degree easily, and much easier because the people they dealt with there, the Mac McNeils, the Gordy Wallace, the Ken Alcotts, Bruce Wright, who the heck was the other one in there? Oscar Tate. And then there was that other dillweed that thought he was God's gift to the world. But all of them tried to get some type of basic experience. Ron Davis. He was an arrogant jackass, but he did try to get some practical experience in there. The problem of it was, he still had his PhD attitude, or his master's degree attitude, whatever it is he had, and he would not listen and would not learn. It was going to be his way. Well, if you've been doing it for, say, 5 to 10 years, then you tend to get let go on your own, allowed to do things on your own and make your own decisions. But if you haven't been doing it consistently and you're out there on a baler knotter arguing with the expert on the baler knotter, yeah, you're an idiot. But he tried. I'll give him that. Because after that, crew fell right down. Gone. I forgot John Posson in Small Engines. Oh my goodness. He says, I know I have PhD talk. That's just the way I am. But for crying out loud, I came out with an associate's degree like everybody else. You had to know John. He was a down-to-earth guy if you talked to him. But he did like to throw out the BS words all over the place. We had a lot of fun. Anyway, you folks have a good night. Behave, be good, be decent. What's today? May? What is that? Oh, I got to get my glasses out. I'm just filling time in to get this near an hour because it's going to take 2 hours to download it. Oh, let's see. May 26th, Friday. That's what it is. 22:19 hours. 58 minutes and change. There you go. Did you get your money's worth? I hope so. And remember, when it comes to electronics, one of the things you have to, why I get so pushy about specs and schematics and diagrams, when it comes to electronics and these newer engines and other systems that all combine with their software, you're working in some cases with 5-volt signals. And they don't even care what the milliamp load is, because you're reading voltage to find out what the signal is, or even the signal load or loss of signal. Can high, can low. And that's something else we can get into later. I'll have to go back and restudy it. I understand it, but practical working? Catch you later.